Testing, testing. Unstructured data workshop. Testing 1, 2, 3. Testing.
Okay, cool.
It's
Hello. Hello, everyone. Welcome. All right, we're going to get started. If you want to grab a seat and start to quieten down. I'm going to do a quick A/B test here. I wanted to welcome everyone to the peaceful hills of Palo Alto. All right. I wanted to get a very big, raucous welcome for an exciting night of discussion on AI agents, and how we implement this. So welcome, everyone. Yeah. All right, we're going to take B on that. So thank you for the feedback. No more peaceful hills welcome. My name is Luke Nixon. I am the head of strategy and operations for SAP Labs in the US. If you're not aware of what SAP does on the development side here in the US, we have about 3,000 people working in development, about 5,000 people working in product across the country. And that's out of a global development workforce of about 40,000 people. And our aspiration is to be the #1 company in enterprise applications. So really glad to have everyone here today, and welcome you to our Palo Alto office. Really excited for the agenda that our partners at Zillus have put together here. So really excited to hear from Stefan, as well as Harry from OpenAI. Later on today, but really just wanted to quickly take a chance to welcome you. Great to have so many people here joining, giving the energy here. So hopefully you get everything that you need out of the evening as well. And again, thank you for making the time. Thanks for making it up here on the hill in Palo Alto. And I'll pass it over to Stefan.
Thanks so much, Luke. So a really warm welcome to everyone. Thanks for coming. And thanks to SAP for having us tonight. So I wanted to, so firstly, just wanted to mention, make sure you star Milvis to enter a raffle for some really awesome swag. But wanted to start off with a question. So, and the question is, how much data produced in 2025 will be unstructured data? What percentage? Does anyone have a guess? Close, so we got 80%. Was it? Between 80 and 99? Well, that's very close, so I'll call you the winner. Actually, 90% of newly generated data in 2025 will be unstructured data. And so that motivates, well, that relates to our mission here at Zillus. So our mission is to help organizations make sense of all of this unstructured data with our vector database technology and our other initiatives. So Zillus was founded in 2017, so well in advance of the generative AI boom. Headquartered in Redwood Cities. Milvis is our open source vector database, and we'll be talking a lot more about that later on. But I wanted to just sort of introduce myself and Harry from OpenAI, our other second speaker tonight. So firstly, so a bit about myself. So my name is Stefan. I'm a developer advocate with Zillus, the company behind the open source vector database Milvis. And as a developer advocate, it's my role to help bridge this divide between users and developers. And so to help you folks get the most out of Milvis, how to overcome your technical hurdles, how to build some really cool stuff with vector databases. So really love meeting users. I love hearing about what your use cases are, and I'm hoping to meet a lot of you folks after the talks today. But I wanted to welcome Harry Zhao from OpenAI. So we're very, very fortunate to have Harry. He's a member of technical staff at OpenAI on the team that was working on deep research. Has anyone heard of deep research? Yep, of course you have. And so he's going to be talking about reasoning foundation models. So from O1 to O3, how reasoning transformed AI and launched a new generation of agents. So can we give Harry a round of applause? Welcome him to the stage. So log into the Zoom.
Oh, I could share screen on Zoom.
Yeah, and share your screen over Zoom. Okay. Just bear with us, folks. While we're doing this, I might actually give you your prize for. Oh, there you go.
I think it's this guy. All right, cool.
Hey, do you want to use the presenter remote?
Sure.
Just plug this in. There it is. And if you want to listen, there's a timer there as well.
Where is that? Oh, I
there.
see. How do I do this? Just like,
it just helps me out, So yeah.
Nice.
Okay, awesome.
Thank you.
Take it away.
All right, hello. You hear me? Seems like you could. All right. Thank you for coming. Thank you for hearing me talk, at you for, I don't know, half an hour. I'm here to talk to you a little bit about agents. I have to slap the slide in front because legal tells me to, so please just bear with me. I might say things that aren't totally public yet. I might say things that are about our products and they may change, so they're not promises, blah, blah, blah. Get that out of the way. There's the agenda here today. I wanted to mainly talk a little bit about how agent building has changed over the past, I don't know, year and a half, 2 years, and why the changes are happening and how you might want to take advantage of these things. And Stefan introduced me, but yeah, I'm currently at OpenAI. I work pretty closely with Deep Research. We developed the newest agentic capability, and a lot of that is really exciting to me, and I would love to share that with you today. So there's a decent amount of slides here about OpenAI and how we kind of operate, and I will talk through them rather quickly and leave time at the end also for questions about specific implementation details or anything else that you guys want to know about. So at OpenAI, we do research, apply, deploy, and repeat. And the product offering here is quite diverse and sometimes very cumbersome. Everyone knows about how painful the model pickers are, so we're working very actively to resolve that. But there's also some really cool products here that would help you in terms of building out agents. We very recently, I think a couple of days ago, launched the Responses API, which is the new agentic platform that helps you call APIs which have tools built in, for example, the Browse API, for example, the File Retrieval API, that allows you to build greater layers of abstraction for you, and as a software developer, abstract away some of the nitty-gritty details of fetching, another browse service and feeding that data into whatever model you might be calling and dealing with all the headaches that come with that. We are abstracting that away, and more API capabilities are definitely coming. So this is an exciting time to build agents for sure. And here's the paradigm that we've been kind of thinking about. We have humans, AI assistants, and automation, right? You have assistants that help the human in making decisions. For example, your copilots, of the world, your document extractors of the world. But there's automation agents that call tools that can actually perform actions. And as we all know, the agentic capabilities is literally just the AI kind of being able to call certain tools at its disposal, and the way we chain those two tools together and the way the tools have the kind of capabilities we enable by the tools allow for these greater degrees of automation. So here's an example of how a customer support kind of use case get built. You have at the very first layer, a tier 0 triage, which is just an intent determination. You get some details about what the customer wants. You have a tier 1 support, which, solves your lower complexity cases. For example, if the user is on your website asking the chatbot, how do I reset my password? It's as simple as go to this link and there's documentation about it. And the higher complexity cases, for example, how do I get a refund for this thing I bought, get escalated, which to tier 2, solving higher complexity cases. And also having this, once you resolve the case, you want to add a layer of root cause analysis. Why are people generally returning things? Why are people kind of performing certain patterns of actions that we don't want them to, and how we could improve on those in the future? And this is generally how we see customers and people build agentic workflows. This is a very simple example, but you could imagine this thing being branched out into multiple layers. So I guess before 2022, even circa 2023-ish, when GPT-4 kind of came out, I think this is still the paradigm of, hey, we have humans in the loop for all of these, and we have at the end some sort of assistant that does this root cause analysis. Basically, your GPT-4 kind of text to SQL agent that helps you write SQL queries and find out what's wrong with the data in your database, or analyze what's wrong with the customer behavior pattern from your database. And now, I think in 2022, this paradigm has been moved over to this phase 2, simple automation, which you have your intent classifiers that get built in. You have your support agents, GPT-4-ish models could do this, or 4.0 for sure, where, for most cases, you can determine, hey, the customer is, this case is either resolvable or needs escalation into your manual processes. And this tier 2 and case resolution is still being handled by the humans within an operations firm. And this root cause analysis, we can have agents and AI help you perform, again, more sophisticated SQL agents, whatever, that live in the backend that helps you out. And now we're seeing a lot of people kind of move into this automation by default kind of paradigm, where the easier stages, tier 1, tier 0, tier 1, is completely being automated away. And we have tier 2, the support, being kind of done along with AI, and the case resolution step done along with AI. And the automation steps are greatly enabled because of this reasoning paradigm, because the models are kind of more capable in terms of figuring out, hey, this is what needs to be done here. And since the model gives a more thoughtful answer before it, spits out a response, it is able to kind of determine step by step what the user needs and what this specific conversation needs without a lot of hand wavy. I remember a year ago, you would have to ask the model, hey, think step by step, think through these cases before coming up with a response, and you would write some crappy string extractor to extract the final response from the model. And now that's no longer the case. People don't need that anymore. The reasoning models already accomplish this by default using their chain of thought. So that's really powerful a lot. And the reasoning steps within get way more powerful because the training process no longer kind of regulates what the reasoning steps end up being, and the model is allowed to kind of drift off in its own thought and figure out the problem at hand. And generally, the reasoning unlocks are just much more powerful than your traditional kind of text-only output models. Oh, I am very sorry about that. Okay. We'll work with that for now. This is kind of the architecture that we've seen people build a lot, which is, you have your 4.0 minis on the front, kind of building your intent classifier. small models are very, very decent at that already. You have your 4.0 models that are kind of using the function calling, and you have your knowledge bases. You built some vector retrieval thing that acts as a knowledge base that gets piped into your 4.0 model. And when you have your human plus assistant layer, you have the 4.0 assistants act as kind of a co-pilot for the customer support case that you're doing. So I guess and actually, let me go back to the slide. I think right now with, tokens being cheaper and models being more capable, you could see the GPT-4o models being replaced by, your O series models, O1 and soon to come O3. And you can have even at this step here, where it says GPT-4o Tier 1 assistant using RAG, we already have the responses API. You could start building, the file with file retrieval. So you could start building this step as just one singular step with the reasoning model that will unlock even more cases and allow you to have greater development velocity here. And you have these escalation cases where it's a tier 2 human plus assistant, but now, you could imagine an O1 model kind of coming up with a response and having a human just moderate responses, whether or not they're good, and override if necessary. So we've been seeing customers switch to these kind of paradigms, and it's been working out great for them. The design principles that we kind of advise people to take is, one, start with the outside in. You start with the lowest risk areas to kind of automate away. For example, the intent classifier, everyone knows, like, hey, this is very easy. You can automate this away, no problem. And you measure out how much that actually changes your user adoption, your user behavior, and see whether or not that gives you the outcome you want, and work your way up from your lower complexity cases to your higher complexity cases. And the second step, log everything, just generally good software engineering practice, especially nowadays when these AIs are making decisions. They're reliable, but when you are on a bigger scale, for example, if you handle, I don't know, 1 million cases every day, even if it's just 0.1% of the cases that go not your way, and the models sometimes generate out of distribution kind of examples that you don't expect, it still happens. Like we've trained internally, Deep Research is a very good model, and even then we've been seeing it output, let's say, a tool call that wasn't within its trained amount of tool calls. It's very, very rare. There's 5 cases per like 1 million, but it does happen because at this kind of scale, the probabilities just manifest themselves. So this, I think, even as reliable as AI agents are, we always have to be a little bit more careful and log everything, and retroactively, at least if you're working with scale, to make sure that the models are behaving the way you expect, and on the edge cases, make sure to handle them. They're not 100% reliable yet, and I don't think they ever will be. And yeah, the third part is just straightforward. Start with the assistants, which is humans working with models such that they can do their jobs more efficiently, and gradually, once you see the use cases that are automatable away, and starting from lower complexity ones, then going forward to the higher complexity, that's generally how people are able to iterate on these kind of use cases. So I guess there's a broader conversation of why reasoning is unlocked for agents, because I think, one, the models are just more intelligent, meaning they obey instructions better. They're better able to figure out what the user actually needs and determine the subtleties of the problem that requires a greater degree of intelligence, so such that they can handle a little bit more complexity, and also handle cases where it's not straightforward as like a simple solution. So that's the intelligence part. And there's also a multi-step decision-making part where you have models being able to chain of thought, chain tool calls together. You pipe the tool call results into the model, and then the model reasons about the tool result it sees and sees, hey, perhaps let's say this database query was syntactically incorrect. It sees the error message. It will be able to reason about, hey, this is why this kind of query is incorrect. This is the part where I screwed up. Let me output a new query that fixes that exact error. And this is the reasoning unlocks this because it doesn't have to spit out another tool call with the database query right away, and it has the space, quote unquote, to think about it before it makes an execution decision. And that's a great unlock for the use cases that we're mentioning here. And just as before, the reasoning capabilities also allow for kind of generalizability, where the model has a chance before giving you a final answer to go backtrack and see, self-revise, quote unquote, what it's been doing, which areas it might be incorrect at. This is we've been seeing more of this internally with the better models. Definitely have a greater tendency to kind of self-correct, to figure out and to see, oh, this is the track that I've been going down. This is where it might create faults. Here are ways where I could start thinking about how to backtrack and go down a different direction if necessary. Here's some advertisement on our new agentic capabilities. The two newest things that we launched, Deep Research and Operator, are really cool. If you ask me, they would condense. Deep Research would do hours of research for you, and Operator would allow you to use a computer like a human. And you could imagine. And Operator has recently been launched on the API, where you could imagine your agents being able to search the web, use a computer, look at some sort of information that you wanted to look for, perhaps some sort of internal database, perhaps some other thing, and then making a decision. You could have all of the context of a computer at your fingertip before making a decision, and that, I feel like, is a huge unlock for people building with agents that want these agents to be more capable at solving problems. This is another advertisement slide about Deep Research. This is an advertisement slide about Operator. If you have more questions about these, we can certainly talk. So yeah, this is a very new thing. It just came out. And we have the vision of kind of doing orchestration layers, optimizing data flywheel, doing data persistence. These are things on the roadmap somewhere that we're going to build. We'll skip that one. This is a response, the currently available agent platform capabilities. I don't know how much people are familiar with these. We can talk about these as in Q&A, perhaps, if people have questions. The agents SDK, I think, is open sourced. It will support third-party models, so you could hook up, I don't know, DeepSeek or whatever into your agents SDK if you really wanted to. The other thing that I actually wanted to mention is the reinforcement fine-tuning platform, which is a little bit, when I first saw it, I certainly found it a little bit confusing, which was basically, if you think about the difference between reinforcement fine-tuning and supervised fine-tuning, fine-tunes the model on a specific kind of type of response. It will direct the model to, the way I think about it is, it will direct the model to output a specific format better, a specific style better, but it won't terribly improve the model on the capabilities of certain of the tasks that you wanted to, unless, of course, you have a lot of data. Reinforcement fine-tuning, because it allows the model to output a chain of thought before kind of going to a solution, it will allow for pretty significant performance improvements with fewer examples. This is where you kind of RL the model into, you have question, answer, and then rubric, and you grade the model not on the rollout. You tune the model not on the tokens it produces, but on the result that it arrives at. Because you're grading the model instead of just doing the supervised fine tuning, it allows for, I guess, quote unquote, a greater freedom of expression, and then therefore allows for like a better performance. We've seen people improve model performance on specific domains pretty significantly with 50, 60 data points if they're like diverse enough, because it actually is pretty generalizable training. So if you haven't tried this out and you're building agents, I strongly recommend you go try it out. It will surprise you. And of course, do make good evals so that you know when the model is improving and when it's not. I don't know why this slide is at the end. It should have been at the beginning, sorry. We will skip that one. These are more agent architecture examples. Yeah, this is the one that we could see coming, that you could imagine people building, where you have your agents, they chain into multiple agents who have specific tools that they can access, and you have some agent that determines the intent and routes the information to the agents. And these agents in return have sub-agents that they can call to perform specific subtasks. You can have planning agents and execution agents and retrieval agents and whatever. They all have their own context, they all have their own prompt tuning. You could improve parts of your system individually without having to rehaul the whole system. This network of things really help people kind of, break down what they need to build specific subcomponents, almost like microservices in software engineering. You break it down, you build subcomponents, and you improve and iterate on each of these subcomponents individually. So this paradigm, again, a lot of startups are doing this. It's a great unlock for people trying to automate away complex use cases. And I guess here are some ways where OpenAI can accelerate your adoption of AI. I think the biggest things is actually, sure, like our models are great, our APIs are great, but I think the biggest thing that I would recommend if you are familiar with the platform, to really go try reinforcement fine-tuning. I mean, it's the thing that got us O1, it's the thing that got us deep research, it's the thing that will get you kind of the biggest bang for your buck for the specific use cases and reasoning use cases that you want. That is the end of the talk that I have planned. I'm happy to take questions now or later if we're running out of time.
We got plenty of time.
Oh, yeah.
So the question is, as the LLM's capability increase, would that change agents paradigm? I've used the example for that. Previously, last year, one of the agent paradigms React, where you have one agent, the other agent check the result of the first agent.
Mm-hmm.
Now, with these reasoning models, a lot of this checking already offered by the reasoning LLM. And so it seems to me that React model, it doesn't really hold much value nowadays. Do you think with a continued evolution of the LLMs, would that be also changing of this agent paradigm? So how the agents
Yeah, so I think for the specific case that you mentioned, which is like a checking agent, I think you should never get rid of your mistake checking agent. I think it's always good to have a safety net there. But on the broad level, yes, I think the paradigms will change. For example, your planning agent might be able to chain tool calls in like its chain of thought, and it's going to be able to do the planning and do the execution and check on its planning and check on its execution and do it again until it gets the result that it needs to get. So this network of agents, being one agent being good at one specific task and you chain it out such that it plans, this very well may go away sometime within, I don't know, the next year and a half. I'm not saying this based on some internal model that I'm making a prediction of. I'm just thinking based on the rate at which these models improve, you could imagine easy things that you could imagine that the models will get better at. One, reasoning, two, context length. These two things already allow you to get rid of a good subcomponent of the agent. And I would actually, the thing that I think that I would advise when building is think about where the model is kind of going to be, at least hypothesize where the model is going to be 6 months from now, and build in accordance to that. Of course, like your predictions might not be correct totally, and you will have to adapt, but building in accordance to that is, and if models get significantly better in 6 months and your use cases get obsolete, then you should really think about what you're building. If the entire agent framework you're building is based on the limitations of existing models, for example, if you're building some agent framework that because reasoning models can do this, can do that, you're building this network of agents to support this, well, I would think that if the models get way better 6 months from now, is this thing going to be obsolete? And if yes, maybe like not build that thing.
There's time for one more. Could you
Sure.
question? Before you
Yeah, sounds good. Yes.
You mentioned supervised fine tuning isn't always needed, especially if you don't have a lot of data. But if you do have tons of data, I guess can you share some use cases where supervised fine tuning might be an unlock?
Yeah, so the question is, basically I mentioned something about reinforcement fine tuning. If you don't have a ton of data, and the question was, if you do have a ton of data, why would you want to use supervised fine tuning versus reinforcement fine tuning? The distinction there, and I think the short answer to that is it's two different types of data also. Like reinforcement fine tuning, you need task, result, rubric. And supervised fine tuning, you have question, answer, response. So those two are kind of two different types of data, and you might have to determine which kind of data you collect and what kind of data you have at your disposal. Of course, you could turn one into the other, right? If you have task, result, rubric, you could turn it into task, answer. But I wouldn't advise you to do that. I think the way that we think about supervised fine tuning is it should nudge the model in a specific direction of response. In terms of style, maybe in terms of content. And it's a more rigid type of thing. You will sacrifice kind of generality for specificity, versus reinforcement fine-tuning will extend the model capability in a certain area that you want, and while also extending the generality of that specific direction, but at the cost of the specificity of the response. It's not going to, unless you have very detailed rubrics about the response format or something, it's not going to give you the exact response that you want it to. As in, it will give you some things that are outside of your format, for example, versus supervised fine-tuning. If you fine-tune it enough, it will give you exactly the thing that you put in the response. Does that kind of answer your question?
It does. Thank you.
I think we're at time here. Thank you so much, and I'll be also just hanging out here for additional chats, questions, whatever. Thank you.
You want to stop sharing the screen?
Yeah. Cool.
Thanks so much, Harry. Really great talk, really great insights into how we're going to sort of, build in a novel way with these reasoning models. I really love this idea of fine tuning on a very small amount of data. I think, and that's sort of performing really well. I think that really lowers the barrier to entry for many applications. Okay, so I just got to set up my text, so bear with me. And then we get on to the hands-on part. We're going to do some coding. Okay, so, but before we get coding, I wanted to say a bit about Milvus and yeah, tell you a bit more about like what it's about, why you should use it, and so on. Before we do that, so I've got my QR code on LinkedIn. Really love connecting with you folks, so really welcome sort of connecting on LinkedIn and looking forward, have a chat after the workshop. But let's talk about why Milvus. So I mentioned at the start that 90% of new data in 2025 will be unstructured data. And so that sort of begs the question, how are we going to get all this derived value? And how are we going to sort of apply our applications on top of this? And as I'm sure everyone here knows, the answer is deep learning. And so using deep neural networks to embed these images, video, text, etc., into these vector embeddings. And then it turns out we can use this, well, one of the ways we can use the vectors is we can look at similarity in space as having like a semantic relatedness. So vector search is the new standard. But this sort of necessitates new tools, and especially the vector database. So vector search is the new thing. So, but how are we gonna search through these? How are we gonna store them, index them, if we have say 100 million, a billion, or even a trillion? Well, this is where a vector database comes in, and why we developed Milvus. So Milvus is the most widely adopted vector database, fully open source under the Apache 2 license. And when I say most widely adopted, that's sort of, we can actually quantify that. So if you look at Docker pools, forks, I believe PyPy downloads, as well as the number of stars, it has the biggest open source community around it, which we're very proud of. And it's built by a team of database experts who have a sort of background in distributed systems and have been able to use that knowledge to engineer a specific database that really scales. So high performance, scalable, and highly available. And so here's just sort of like a little diagram of the architecture. So in the fully distributed version, which you can deploy, it will scale to literally tens of billions of vectors with sub 10 millisecond latency. So you'll have a deployment that has a distributed system looks a bit like that. So you can see there's all sorts of different nodes doing specialized things, passing messages to each other. The separation of storage and compute, that's another really important design principle. Milvus has a really rich functionality. So if you want to do something with your vector database, it's most likely that Milvus has that implemented. So for example, in one of our recent releases, Milvus 2.5, we've introduced a text search or a lexical search. So you can use Milvus to replace your more sort of like standard lexical search database, and just have one database that you can use for both semantic search as well as lexical search. And that's why many industry leaders are using Milvus to solve their hardest problems. So everyone from Salesforce to Bosch, having these really massive deployments, 12 billion, 20 billion, they depend on this every day. And we're really proud to call amongst our users some really big names, Microsoft, NVIDIA, Airbnb, IKEA, just to name a few. So Milvus has a really good scalability, but when you're prototyping, you obviously don't want to sort of start off at that 10 billion scale. So Milvus has 3 different deployment types. It has Milvus Lite, which is a version we'll be using in this workshop, which you can load. You can very simply just install a Python package and work in a Jupyter Notebook. And then there's Milvus Standalone, which runs via a Docker image. And this is really good for sort of like larger scale prototypes, as well as medium-sized applications in production. And then we have the fully distributed version, which you'd launch via Kubernetes and really scales massively to the tens of billions of vectors. Okay, so because it's open source, Milvus has a fantastic integration across the generative AI technology stack. So having the largest open source community, we've had a lot of integrations contributed. So if there's some other tool that you use in your workflow, most likely there'll be an integration. But let's move on to the demo. So we were very excited when Deep Research came out. I think it was start of February, and it inspired us. Well, it inspired quite a few people to sort of try and reproduce some of the functionality, some of the results. So that inspired us to develop a research agent of our own. And obviously, it's not like a fully it's nowhere near like the performance capability of OpenAI's Deep Research, but I think it illustrates a number of very important principles in building agents. So I think it has a really good pedagogical value. So what's important about research agents? So I've just taken some quotes from the blog post release for Deep Research from OpenAI and tried to sort of like categorize them. And I picked out some common themes. I think one is like this iteration, learning to plan and execute a multi-step trajectory via the reinforcement learning that's happened on the reasoning model. The search, so being trained to for this tool usage, browsing the web, and then these things sort of overlap, and then just like reasoning more generally. So this is an architectural diagram. So before we go into the code, I think it helps to have a higher level picture of what we're building and how it works. So this is like an architectural diagram for Deep Searcher. And you can see it has two main parts. The first part is data ingestion. So for this system, we're actually going to get all of our data in advance. Maybe in like another system, you could introduce web search as a tool and fetch additional data as needed. But we're going to ingest and index all of our data in advance, and then store that in our vector database. And once we've done that, then we can serve queries. So imagine that the user comes along, they have a query. In this particular design of a research agent, these are the steps that we follow. We take the query and we break that down into a number of subqueries to answer that question. Then we look up the vector database. So you can route it to several different sources using the reasoning model. We then look up relevant chunks in the vector database, and then do some reflection. So given that we've retrieved that knowledge from our vector database, and these are the specific subqueries, we ask the reasoning model, are there any knowledge gaps? So is there anything left to fill in? And so it has to reason over the queries that it's answered so far, as well as the retrieved information. And so this is sort of like where the conditional execution comes in, if you will. So it may say, yes, here are some other questions that we need to answer to fully answer the overall question. Or it might say, no, we've retrieved enough information to write our report, so we'll terminate, we'll exit that loop, and we'll go on to the final report writing stage. And here's like a really quick illustration. So this is, you can check out Deep Searcher on GitHub. The link is in the notebook that I'll provide very shortly. So we may give it a query like, write a report comparing Milvus with other vector databases. So here's the query. And then it breaks that down into a number of subqueries. And then asks, it thinks what it needs to do next. It needs to perform a search on the first subquery question, and then do a vector search in both of the sources. So there's Milvus docs and what is Milvus. It has two vector DB collections that it's routing to. So then it repeats the same thing. It searches the first subquery, but data from the second source. And then, so now I can move on to the next subquery and essentially just repeat those steps retrieving all of the relevant information to answer that question. And then it does like a few steps which are not sort of like shown in the output. So it's going to do some re-ranking and say, is this chunk that I've retrieved relevant to the question at hand? So sort of like, yeah, like a re-ranking step on top of the vector database retrieval. Okay, so now we just repeat that for all of the subqueries, and then it does this reflection step. So it reflects, okay, have I answered all the questions that I need to answer to fully to write this report? And so in this case, it says no. So here are some new questions for the next iteration. And then it just goes through the same loop a second time, answering these new subqueries. So I'll just sort of skip through these lines. And then once it's done that, then it does another reflection step and says, okay, I believe I've got all the information I need to answer the report. So I'm going to go on to the final step, and I'll write the report. So the conclusion, so Milvus is a compelling choice among vector databases, noteworthy for its high performance, flexible deployment options, yada, yada, yada. So you can see it's retrieved the ground truth. Okay, so let's build it ourselves. And when I say let's build it ourselves, we're going to be implementing the core functionality, but with all of the bells and whistles removed. So it's really just the bare essentials. And I think that could really sort of illustrates the principles at play. And this is just like a really sort of basic design of a research agent. So something that we chose. There's no sort of like set formula. That's something that different teams would make different choices on that. So I want you now to open up this Google Colab notebook. So I've got a bit.ly code as well as let me move my picture. Okay, and a QR code on the screen here. And I just sort of thought, actually, once I move off this slide, how are people going to open up the notebook? So I'll just keep it up here for a few minutes. If you miss out, ask someone at your table to pass along the link. And so once you've done that, open up that Google Colab notebook. So is everyone able to open that up? Okay, awesome. And then, so if you want to follow along, so the first step, the data ingestion is not that interesting. So I've done that in advance. So the data we'll be using is the Milvus website. And basically, I've done a full scrape, the Zillits website. I've done a full scrape of the Zillits website. I've then chunked it, turned it from HTML into Markdown, and then embedded those chunks, and then saved that into like a data set file for easy. You can open it using standard tools. So we'll be using the Hugging Face datasets library, for example. Okay, so I think I've given everyone enough time. So now I'm going to actually move across to. Okay, so let me show you the data ingestion at like a very high level. This is just like me hacking something together. So just imagine you sort of, like writing a prototype. So essentially what I did was I just took, I wrote like a spider to scrape the sitemap for Zillits.com. And then I turned that into a link of URLs. And so that outputs this list of URLs. So these are all the URLs that are given via the sitemap. And then I take those and I actually, so I could have done the step in the spider. I'm just sort of like hacking something together. So as they say, do as I say, not as I do. There's some quick and dirty coding practices here. But I loop over those URLs, I download them, I convert them into HTML, and then I chunk them with LangChain. So break them up recursively into a number of chunks. And so it turns out that, so the Zillits.com website, so just to give you a sense of the scale, it has 28,500 URLs. And that translates into a bit over 300,000 chunks. So, this is like, not like a massive scale. We'll still be able to use Milvus Lite and do this all in our notebook. Okay, but going over to the main notebook, so this is essentially the Google Colab that you guys are viewing. So if you haven't already, download the Zillows.com dataset. So that's what I've put together. I've done the chunking and the embedding already. Okay, so with that done, the first step is to read in this dataset file and just like have a look and see like what's going on. So now I'm going to slow down a bit and I'll be going through the steps at a more sort of like leisurely pace so people can follow along. So just to make it, so that I'm not cheating, I'm going to restart my kernel. Okay, so we import our libraries. So PyMilvus is the Python client for Milvus. So it's how you connect to a Milvus database with Python. And we'll be using some other standard tools like, libraries like Pandas. So this file, it's in a Parquet dataset file. So the first thing we'll do is we'll read it in with Pandas. And then we'll just print off the head. So you can see that this dataset file, as I've set it up, has 3 fields. It has the text. So this is the text of the chunk. It has the source. So this is the URL that chunk came from, as well as the vector embedding. So I just use like a common model from sentence transformers. Again, like not that interesting. I did that at home using my GPU. Okay, and then we can see that as we expected, we've got 312,000 rows. By the way, is this size big enough for everyone or should I make it a bit bigger? Bigger? Okay. Geez, can I do this on the fly? We've got some Visual Studio Code experts in the audience here. Thanks so much, Dan. Righto, so we've opened up our database. We've just had a look at a few entries. We can see like what's actually got inside. Let's now put this into our vector database. So the first step is we have to create this Milvus client object. And this is going to be like our interface to the Milvus vector database on our local system. For the URI, we put in a file name. And that's how PyMilvus knows that we want to use Milvus Lite. If you put in a URL, port number, etc., then you'd be able to connect to like a remote deployment, Milvus standalone running on Docker, or Milvus distributed running via Kubernetes. So we'll open that up. And so now we have to actually, sort of do a bit of housekeeping before we can use our vector database. So I'm going to create a schema for each entity in the vector database. I'm going to create an index. And then I'm actually, so once I've done that, I can create what's called a collection. And a collection is essentially like a table in a relational database. So we tell it what the name is, what the dimension of the embedding is, what the primary field name, what is the vector field name, etc. And then we'll then be able to start putting stuff into this. So let's run that. Okay, so and just for debugging purposes, I printed out that we now have a single collection called default in our vector database, which has the right schema for us to start putting this data in. Okay, so now essentially we just need to iterate over our pandas data frame and insert these into the vector database. I'm doing it in batches of 1,024. I think it actually might be faster if I 10,000, just to make this a bit, I think this will make it faster. Okay, so hopefully this step might take a minute or two, but luckily, as they say, here's one I prepared earlier. So I'm going to load up. I've actually saved my database file from earlier. And if you just want to start from this step, you can go up the top and you can just download that pre-built Milvus Lite database file. Well, actually, let's see how it's going. Yeah, I'm going to kill that, and we'll open up our pre-built vector database. So just going to change this line to the file that I've already created. Oh. Doesn't seem to like that file name, so I'm going to put an underscore in here. And by the way, if anyone wants to like stop me at any point, am I going too fast, too slow? Just so we can adjust things. Okay, so this is the database that I cooked up at home, just by running this cell, looping over the rows and inserting them. And just to make sure, I'll run this line here to see, okay, so what this says is in the collection default, we have 312,000 rows. So I know that there are as many items in the database as I was expecting. Okay, so we've got our vector database. Now we can actually start integrating this into a simple agent. And so we're going to be using, to search this vector database, we have to load up the same embedding model that was used to create those embeddings. And so I know that the one I used was All-Mini-LM, a standard one from the Sentence Transformers library from Hugging Face. So I'm going to load up that library. Has anyone got any questions at this point? Okay, and so, you know, this library, I think it's, oh, sorry, this model, I think it's like maybe half a gigabyte or something. So, oh, there we go, it's loaded. And now, just to sort of, you know, test things out, I'm going to do a simple search on our database, just to check that everything's working nicely. So to do a search, we have to take our search string, and then we have to embed it. So I use that model. In this case, the search string will be comparison between Milvus and Weaviate. So that will give us back a query vector. And to do a search, a semantic search, or a similarity search in a vector database with Milvus, we use this Milvus client.search, and then we just pass the collection name, the vector to search for, the fields we want to output, as well as some other items. Okay, so that search finished. Let's see what it gave back. Yeah, so you know, it looks like it's retrieving chunks that are related to Milvus versus Weaviate, and you know, Milvus versus other data sets. So my vibe check is that our vector database is working. Okay, so now let's actually build our agent. And so when I say that we'll be building a simpler version of Deep Searcher, what I mean is I've copied the prompts out of the source code for Deep Searcher. So we'll be using the same prompts as well as more or less the same like sort of agentic workflow. So let's look at the prompts that we've got here. So the first prompt is going to help us take a query or a question and break it down into a number of sub-questions. So the prompt goes a bit like this. To answer this question more comprehensively, please break down the original question, yada, yada, yada. And then when we format it, we put in the original query here. And we give it a few examples. So doing some in-context learning. And instruct it to return the response in Python code as a list. And so, this is just like a system I hacked together quickly. Obviously, like in a production system, you would want to use some sort of library or function for constraining the output so that you know it's going to be well formatted Python code or JSON or whatever. Okay, so that's one of our queries. Then we'll have a re-ranked prompt query. So this one goes like this: based on the query questions and the retrieve trunk, to determine whether the chunk is helpful in answering the question, you can only return yes or no, yada yada yada. So this is going to help filter our chunks. So vector search is much more, I guess, sort of like a rough, inexact type of retrieval. It helps to do some re-ranking or filtering with a large language model or a foundation model on top of that. So we're going to take each of the chunks that we've retrieved from the vector database, and we're going to ask the reasoning model, does this chunk help to answer the question? And so next prompt is reflect. So this one essentially says, are there any gaps in our information? So determine whether additional search queries are needed based on the original query, previous subqueries, and all retrieved document chunks. And then if so, please provide a list of up to 3 search queries for the next iteration. So this is going to be the step that sort of like controls the execution of the loop. So the reasoning model will be able to sort of like keep going in that loop if it thinks there's additional subqueries that need to be answered, or else it will be able to terminate, and then we can go and write the report. And then finally, we have the summary prompt. So this one goes like this: you are an AI content analysis expert, good at summarizing content. Please summarize a specific and detailed answer, yada, yada, yada. So this one, it's going to take all of the information that we've got so far and then ask the reasoning model to synthesize that into a report. So it'll have the original question, it will have all of the sub-questions, as well as all of the filtered related chunks, and use that, synthesize that into a report. So now I'm actually going to run this live. So hopefully this is where things always break for most presenters. Okay, so we'll be using OpenAI's O1 mini model. I've just like hidden my API key here. If you're curious, I think a simple query running report took, it's about like 10 cents with this particular workflow. So yeah, not to worry about like inference blowouts. Okay, so let's just test our OpenAI API, make sure that we've got everything set up nicely. So here's the set, just like a test question: write a 1-sentence bedtime story about a unicorn. So this is the amazing age we're living in. We can automate tasks like this. And let's see what happens. Okay, so under the silver moonlight, a graceful unicorn, yada, yada, yada. So it looks like we can call our API key works, which I've hidden, and we can call that model. So let's move on to the actual loop of the agentic workflow. And the query that we're going to be answering is the same as the one that I showed you in the example output from Deep Searcher, which was write a report comparing Milvus with other vector databases. And so, I'm sort of like prototyping the system. Obviously, like some of this code is not best coding practices. You would want to like break more stuff out into functions. You'd probably want to use like a higher level library to implement this agent if you were doing it yourself. But I'm sort of like doing things sort of without any like additional layers of indirection, so you can really sort of like understand the principles. Okay, so firstly, we take that query and then we turn it into our subquery prompt, which asks the model to break it down into a number of sub-questions. And so I've got a bit of a hack here. So these two lines essentially take the output from OpenAI and convert it into a Python list of strings. And I'm sort of like relying on the fact that OpenAI if you ask this model to give you output in a certain format, it's very likely going to respect that. But obviously in a production system, you would want to use maybe some sort of like a additional feature or library to make sure that your output is well formatted. Okay, so we do that. And then it's broken it down into these 4 sub-questions. So you can see that like these are sort of like orthogonal sub-questions that help us answer the main question. And now this is where the actual sort of like meat of the agent's going to happen. So what we're going to do is we're going to loop through the subqueries. And so while we have subqueries, we'll be performing that loop that I showed you in the diagram. We'll be doing a vector search, retrieving relevant chunks, filtering those chunks, and then asking the model to reflect, does it have all the information that it needs, or does it think there's some gaps in its knowledge? So I'll just go through the cell before I run it. So it's looping over. So while we have subqueries left to do, so we'll take those subqueries, we'll encode all of them in one go, then we'll perform the Milvus search on each of those subqueries. So this is going to return like a list of results. And each of those will have three of the closest matches from the vector database. And if you recall, our vector database contains the entire Zillits.com website. Okay, so now we've retrieved those results. So what we do is we loop through them and then do some, I think this is just doing some simple sort of like getting them into the format that we want. We're putting the chunks into a dictionary where the key is the ID, the primary key, and that helps to deduplicate. We're probably going to retrieve some similar chunks from our different subqueries. And then we can do the filtering. So I've defined this filter function here. This filter function, it runs a re-rank prompt. And then, so again, like I'm using the fact that this output is going to be, it's going to be in the format that we ask it to because that's just how O1 Mini works. So my little hack here is like, if there's a Y in the response, then it must be true. And then I apply this filter with a dictionary comprehension. So I just sort of like loop over the chunks, run this filter. If the filter is true, then we keep them. Okay, and then we take the filter chunks, we add them to our dictionary of all the chunks that we've seen so far, as well as we update our set of subqueries that we've seen so far, because at the end, to write the report, we'll need access to all of them. And then we can ask the model to reflect. We can run that reflection prompt. We give it the original query. We give it the questions that have been asked so far. We give it the chunks that have been retrieved and have been judged to be relevant. And then we run O1 Mini model again. So, I think I should have just like broken this out into a function, but I think just like when you're sort of like doing some quick and dirty hacking, this is what things look like. So we run that reflection query, and that query will return either a list of new subqueries if it thinks there's gaps in our knowledge, or just like an empty list if it thinks that that's finished. So that's what this condition here says. So if we have subqueries, then we'll just print them out for debug purposes. Otherwise, we'll print no new subqueries. And because of the condition of the loop, while len subqueries, it will then terminate that loop. So let's run this, and hopefully nothing breaks. Okay, so it's broken the query down into the original subqueries, retrieved the chunks. Now it's calling the model on each chunk to work out, like, is it actually relevant? So you can see that 2 of the chunks it's going to discard. Okay. This might take a little while. So how are people going, by the way? Any questions so far? Yeah, of course, yeah. So the question is, when do you choose to have like your data ingested in advance, like we've done here? And when may you actually use like web search as a tool? Yes, I mean, I think it's sort of, okay. What we've done here is we've like amortized the cost of scraping the whole Zillits website and putting that into a vector database. I don't know if I want everyone here simultaneously scraping the Zillits website. Might not be the best. So I think like the answer is like a combination is ideal. So to build like a more sort of like, I guess like sort of the version on top of this, we might add like web search as a tool. And it might say, so we might give that the agent the option to say, okay, I'm actually going to perform a web search now. But you know, something like an internal application, it's, you know, your website's probably changing much less often than like the web as a whole. Yeah, so exactly. So yeah, those are two good examples. So internal websites and other things, maybe like images, sound, video, that are a bit more static. Okay, so while we were having that discussion, it's been reasoning away and reflecting. So it went through the first iteration, and then it decided, okay, there's actually a few gaps in my knowledge. So I'm going to ask these 3 questions, go through that again, filter the chunks, and then after the second iteration, it says, that's enough. Like there's no gaps in my knowledge, so I'm going to terminate the reasoning loop. So now we can just go ahead and generate the report. And the report will take all of that information over this, these loops of the agent. So we'll put in the original query, we'll put on all of the unique subqueries over all of those loops, as well as all of the unique chunks that it fetched. And then, so we'll run that prompt. And this should be fairly quick. So for anyone here who has an OpenAPI key, have you been able to run the model? Have you been able to get up to this point? Yep, awesome. Okay, so this one was a bit longer because it had to generate a lot more tokens just by the nature of the query. It had to input a lot more tokens too. So let's output the response. Okay, so this is what it's output. I've just copy and pasted like a previous output into the next cell, and because it's Markdown, it will be able to visualize this in the Visual Studio Code editor, or Google Colab if you're in there. Okay, so let's take a look at this. So, you know, it starts off with introduction. So it looks like it's sort of like giving this a nice structure, overview of Milvus, key features, then going into a bit more detail. So comparing it to other vector databases. So, you know, it seems like it's doing a reasonable job of writing a report. It sort of looked into like the sort of like the sub-questions that we need to fully answer the overall question, and then synthesize that into like a logical structure. So, you know, you might be like curious to try it out with your own queries. Does anyone have any suggestions? We could do one live. Okay, maybe for time purposes we won't. So that's it for the notebook. So hopefully you learned something. This is just like a really simple example of how you can use a reasoning agent to construct like a research agent that can do useful things and write reasonable sounding reports. If you were to you know, build on top of this, you might want to add in other types of tool usage. You know, definitely being able to do web search would really, you know, increase the power of this code. So yeah, that's it for the code part. let's go back across to, okay. So, we built a simple agent. I just wanted to reflect a bit on what some of the challenges are of research agents. So firstly, I think there's sort of like three big challenges. Firstly, just like getting the data to actually train your reasoning models, if you're not using a closed source one, or I think we're going to see more and more really, really high quality open source reasoning models. The second one is the cost. This reasoning agent had to do a lot of calls, a lot of inference, and so that's going to sort of, that's why it sort of might take 10 minutes, half an hour to go off and research this report for you. So there's like a cost aspect there. And then there's just like sort of like scaling, other aspects of scaling that are not related to cost. So more on like the hardware infrastructure side. And I think that's where Zillits can really come in and help. So we talked about Milvus. So that's like the open source version that is self-managed. But we also offer a fully managed service, Zillits Cloud, as well as a bring your own cloud version, Zillits BYOC. You might really want to sort of have a large vector database, but you don't want to do, you don't want to sort of like incur the hassle and the cost of managing it yourself. And so that's where a fully managed service is really helpful. I've added a little link here to the sign up for Zillits Cloud. We have like a free tier offer, which is actually one of the like easiest ways to start working with a Milvus database. So you can click on that link and set up an account. But with that, I wanted to wrap up and say thanks everyone for coming, and thanks to SAP. Thanks Harry, really loved the chat. We've got a bit more time, so we're going to do like a office hours type session at the table over there. Oh, and so I have to tell you, if you starred Milvus at the start, you entered the raffle. We're going to do the draw the raffle right now. Okay, so we've got some cool swag on the line here. Who's it going to be? Okay, we're spinning the wheel. Here we go. Well, quite a few people entered. It's really good to see. Do we have a Sandtire over there? Okay, well, yeah, congratulations. So come and see Sachi at the end, and you'll get your really really cool swag. Should we do it once more? And thanks for starring Milvus, everyone who entered this. Really appreciate it. Do we have a Luo 877280? Well, if you're here, come and see Sachi, and really nice surprise in store for you. Okay, so we'll wrap up the workshop part. And as I mentioned, we'll be doing like a quick office hours at a table at the end there. So if you've got any questions you want to chat about Milvus deployments, OpenAI, come and have a chat, and we'd love to hear what you're building and help you resolve your technical challenges. So thanks everyone for coming. So don't forget, folks, we're doing the office hours at a table over there near the, oh, where is it? Yeah, right here. You see the little flyers on the table. So come over and have a chat.
This is yours, right? I'm not sure.
This one is ours, yes. It has the labels.
Can I remove